Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video we will speak about how to grow a tree or how to learn a tree. In the end, you should understand how a tree is grown by an exhaustive or greedy search, and you should know where and how the split points are set or the split point is set. If we want to grow a tree, so this is the step of learning the tree, we start with an empty tree, so it's just the root node that contains all the data points. The trees are then grown by recursively applying greedy optimization to each node. Greedy optimization means that we do an exhaustive search, so ideally all possible splits of n on all possible points t for all features x, j are compared in terms of their empirical risk. Then the training data is distributed to child nodes according to the optimal split, and the procedure is repeated in the child nodes. Okay, let's see how this works in an example. We start with the root node of all the data. So it's the same data you know from before. The iris data, there is 100% of the data in that root node. Then we search for a feature and the split point that minimizes the empirical risk in the child nodes. So we can, for example, first look at z-power length and split here or there or there. We could also look at z-power width and split here or there or wherever. And for each binary split, we get two child nodes, a left child node and a left child node. And we can then look at the empirical risk in those child nodes and then sum them up or take some weighted mean or whatever and look which of these splits is best. And the best split point is then chosen, and here apparently it was z-power length equaling 5.5, so exactly this split here. Once we have done this, we do this for recursively for those child nodes too. So we first split it here. Okay. So now we have to look at what will we do there. So we compare all possible split points here. So for example, this split and that split, that split, and that one, 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 and so on and so on. And then we figure out somehow that the best split point here apparently is splitting at z-power width equaling 2.8. And on the right hand side of z-power length equaling 5.5, we do the exact same thing. We compare this split and this and this and this and that and that and that and that and so on. And apparently splitting at z-power length equaling 6.2 is optimal there. And then we do this one last time. We split further and get then this surface here. And we can do this until each leaf cannot be split further, for example, because all the leaf nodes are pure. But there are also other stop criteria, which we will tell you later about. Now the question is, how do we split this? How do we place the split exactly? So here this should be an x2. So let's say we have two features, x1 and x2, and we have data points here and there, and these are of two different classes. So this means that for the empirical risk, or for the question of how homogeneous the split splits the data, it does not matter if we use this split or that split or that or that or that, because all these 5 split points achieve a perfect separation of the two data points. Okay, so in terms of empirical risk, it's equally good to use any point between 2.7 and 2.9 for placing the split. And what we do then is we just put the split exactly at the midpoint of the two observations. Okay? Because we hope that if this margin and that margin are at the same time the largest we can have, that this would make better generalization on new and unseen data. And this is of course something that we always want to achieve. So we don't only want to split the training data perfectly or as good as we can, but we want to achieve a good generalization of predictive performance on new unseen data. And we kind of hope that if we place the split between the two observations, that this achieves our goal. So once again, how do we find a split point? So we just try out everything, so as told before, but now here we have some numbers for you as well. So first we just look at z-pile width. Okay, we just look at those horizontal splits. And for each horizontal split, we get the left and the right child node. And then we can look at the misclassification error in the data. It's just computing how many observations are classified correctly and how many are falsely classified, and then we just take the ratio of misclassified points here. And then we can compute for each split point the MCE, the misclassification error, and see, okay, given that we split at the feature z-pile width, then the best split point seems to be something in that order 3.25, because this gives us an MCE of 4.6. But of course, we can do the same thing for the other feature for z-pile length and look at all those vertical splits now. And also for these splits, we get those misclassification errors, and we see, okay, if we split at z-pile length equaling 5.5, the MCE is even smaller than what we had as an optimal split point regarding z-pile width. So the final decision for the first split point will be z-pile length equals 5.5. And of course, in real life, we don't only look at 5 splits in feature 1 and 5 splits in feature 2, but we can, for example, search over all possible split points. So a possible split point would be any point between two observations. Or we could search quantile-wise, so we could set a split at the 1% quantile of z-pile length, at the 2% quantile of z-pile length, and so on. And the same thing for the 1% quantile of z-pile width and the 2% quantile of z-pile width, and so on. So for really huge data sets, I guess it would be smart not to look at every possible split, because this takes some time, but search quantile-wise and for really large data sets. It also usually doesn't make that much a difference if we split at 0.0001 or 0.002. Okay. And one last notion, well, I explained to you now how to use the misclassification error for finding the optimal split. This is usually not used in practice, and we will cover other split criteria in detail very, very soon. But yeah, for pedagogical reasons, we think it's best to explain with the MCE, even if we wouldn't perhaps use this in practice.